generative model, in your generative architecture, we will be considering the negative values because we are predicting the new values based on the existing values. So far, whatever we have done with respect to neural networks or CNN, everywhere we have used a redo as an activation function because we don't need to consider any negative values. But here we are in a place to predict the new values based on the previous one. So in order to create a previous one, in order to understand a previous one, I need to understand even it's a negative value, I need to understand about him to generate a new values. For example, if I wanted to hurry you to my organizations, okay, I wanted to do background verification, I wanted to know end to end about you before I'm boarding into you. So and then only I can able to generate new outputs from you from my organization. So that is the same reason. In order to generate a new content, your architecture should play with all the negative values. That's what we are using the tanh functions right at this place. And here W hidden values of the previous hidden values and the hidden value, the weight of the previous hidden layer and current hidden value. I mean the previous hidden value plus the weight of the current time step neuron and current. Just a second. Yes. Yeah. So now tan h, this is a weight of the previous hidden state, and this is a value of the previous hidden layer value. Plus we have a current value, current weight, current layer weight, and the input of the current input at time step. All together, we can able to calculate the current layers hidden values. This is how we are calculating the hidden values. Okay, and next one is like output. How the output we are calculating this is based on the weight, and as well as the current hidden, we are calculating the output. I'll show you the picture representation so that you can able to understand a better way. Okay, so now, but this is a overall equation where we are using for RNN architecture, which is very important equation. And this is a computational graph with respect to what I have shown in this picture, right? I mean equation, the same thing. Now, if you see in this RNN architecture, this is your previous hidden value. Okay, this is a unit, maybe previous hidden unit, and this is your current function, the equation we are talking about. Okay, the tanh function, and this is a current input at per time step. We have a multiple time steps. Okay, so you are giving the input, and we have a function, and if you see that, you will be predicting the new hidden values. So every architecture in this entire architecture using the common weights. Okay, it will be issuing the common weights across all the functionalities. Because everything is happening one at a time. So this weight in the sense first iteration, during the first epoch it will be happening. So second epoch the weights will change. Okay, because earlier we have seen the neural network architecture structure is quite different, but when you come for the RNN it's quite different. But all together doing the same, but here we are dealing with the cells. Okay, LSTM cells. Okay, so now you see you are giving the weights and we are giving the new hidden states, and through that we are calculating the output. Okay, that means sentence classification. You are giving some English to French translation earlier, right? 2015, 2014, 13 and all, if you go, Google translation, Google text predictions, and Gmail compose, and everywhere what architecture was used in the sense RNN architecture. In Google recommendation, everywhere whatever text related classifications or text related predictions you have seen, everything is based on completely RNN architecture. But now we are using everything is being recreated by the reused by the LLM models. Now Google Test is replaced by the LLM models, and as well as the Google Compose, Gmail Compose is being replaced by the LLM model. Google Recommendation is completely changed by the BERT models. Okay, it has been completely vanished off. These RNN architecture, vanished off in the sense replaced by the RNN architecture. But this is a father of the current LLM we are working. Okay, so now example x1, x2, x3 in the sense nothing but. So you are trying to approach English to French translation. Your English word. This is J, and the translation you can able to express this is J. Likewise, you get the translations. That is what it's trying to say. Okay, everything per time step. Okay, so now if you see, you will be getting the values for each and every hidden state. We will be getting the values. From that value, we are calculating the loss, and all together this loss calculations we are calculating across for all the input time steps and the results, and we are calculating the overall loss. Okay, the approach of RN architecture quite different when compared to this, but this is a very simple. For the one process, the functionalities will happen per input time step. Okay, for each and every input per time step, this process will happen. Okay. So what is tangent function? As I told earlier, tangent function is like hyperbolic tangent function, which is commonly used for whenever you are working with the generative models. It will be supposed to consider from -1 to +1 region, and when you are integrating this tangent function in your hidden layers, it will be started considering even the negative values. Will be considering the negative values. So by using this tangent function, of course, we will be facing a lot of gradient issues. Okay, so what is that? Exploding gradient and a decaying gradient. Many issues we will face, and we'll see how we are handling those. When we are using RNN architecture with a tangent function, you will fall into overfitting. I mean, the gradient issues. That issues relevant to exploding gradients and decaying gradients. How we are handling these gradient problems, we'll discuss that. So where are all types of RNN architecture? So first thing is like a one-to-many. You can give image captioning. You can give one image, it will be giving you the captioning. You can compare with the applications. So whatever applications you are working with, earlier everywhere we have used RNN architecture. Given image, it will be giving you the caption. So a man is standing near the tank and he's playing with a frisbee or something else. Likewise, it will be giving the captioning. And next one is like a many. So this is about a many to many. So many to one. Sentiment classification. You are giving some movie reviews. You are giving a movie reviews. It will be giving you the one result, like whether it is a fake or true, or whether it is true or bad. So likewise, it will be giving you the feedback as a many to one. And when you go for the many to many, it is a frames. So machine translation, you are giving one language and you are parallelly getting the other language. So English to French translation, the dog is walking, and you will be getting the same results in that the dog is walking, the one you have seen in the previous slide. Okay, and the next one is like a many to many. This is nothing but frame level. So in the video synchronizations and all, we are doing it, right? So in video level classifications and video level predictions, everything based on many to many. So where and all you are playing with the text, everywhere RNN was used, and based on their purposes. So image captioning and image classification and video frame level classifications, and everywhere we are using RNN architecture. Okay, so we will be seeing in a hands-on like a sentiment classification. I'll show you about the sentiment classification. And gradient problems. So gradient problems is one of a common problem. If you see, the feed-forward neural networks is to backpropagate and update the network weights. But when you go for the backpropagation, breaks down in the recurrent neural network because of the recurrence and of the loop connections. When you go for the this was addressed with the modifications of a backpropagation technique called BPTT. So backpropagation through time. Okay. So see, in our earlier architectures, the architecture looks was different. Architecture looks was different. You didn't know what is the input layer, hidden layers, everything. But when you come for this particular scenario, the logic itself differs. Okay, here you cannot able to do the back propagation as like we did before. If you do like this, the problem we are talking about, the gradient problems will occur. How the gradient problems will occur? I'll show you the scenario. Okay, so that is what we are using the technique called back propagation through time. So how we are handling the back propagation through time, we'll see. And this particular back propagation BPTT concepts we have created in order to handle the problem of gradient problems. So we have two different gradient problems. So one is like an exploding gradient and another one is a vanishing gradient. Exploding gradient, vanishing gradient is nothing but. So during the time of optimization, right? Consider this is your X and this is your Y. X and Y. Okay, so what is the gradient problem? Since as I told, right, in the optimization technique, initially your loss will be higher. Okay, so over the time period, your loss are supposed to be get reduced. Okay, so what is exploding the since it will be learning, okay, good curve, but over the time period, it will be explode. So this is a call, your error will be keep on higher each and every epoch. Till the last epoch, you can able to encounter the epochs are quite larger. I'm sorry, not epochs, I mean the losses are quite larger. This is called exploding gradient because your gradient problems, I mean you are not able to achieve the good loss over the time period of the epochs. But what is a vanishing gradient? Since you have a xy, and during the first epoch or second epoch itself you will be getting the losses very low, and sometimes you will get the losses as 0, or sometimes it will go sometimes the negative zones, or else you will be looks in such a way. So this kind of problems we will call it as a vanishing gradients. That means this supposed to now during the time of optimization you should not get the more loss, and also you should not get the loss as a 0 or minus values. So this is a problem called exploding and exploding and as well as a vanishing gradient problems. So this exploding and vanishing gradient problems, when it will happen in the sense when you are not doing the proper back propagation. If you are doing the proper back propagation, tuning the values are fine. But in our architecture, we are not able to do the proper back propagation. Reason is our constructions are quite different. Our construction of the architecture is quite different. So how we are handling this problem? This is a simple scenario. If you see that, this is how your architecture looks like. Your previous state, previous cell state information, and we are taking that along with the weight we are calculating, and we are having this results, the functions. Okay, the tan h, weight of the previous state, and weight of the current input. Okay, now we are calculating results. We are calculating the weights of the results with respect to this time state, and we are giving that is on next cell. Okay, based on this next cell, we are understanding this one. For example, the red dog. Consider for the we are understanding some understanding. So some classification or some results, that is our output. Okay, that cell information is going there because in order to predict a new word you are required the previous cell information. Okay, with respect to this knowledge we are having the same function again. The dog value will go and we are predicting the new cell and we are doing this. So this is a usual process. Now how the loss is the same. However, we are calculating the overall output and we are calculating the loss for each and every word, and we are accumulating the loss. For example, the big red dog, and you are translated into French like a ki, mi, sha, something you have translated, and you are having the loss for each and every values. And all together, you will be calculating the loss function. Based on the loss function, you will be doing the back propagation. That is a flow will do. Okay, think about it. You are updating the loss function 0.0001. Okay, so no, you got a loss. And based on that loss, you are about to change the weight of each and every layers with the weight of 0.01. So over the time period, when it's trying to update over the time period, what will happen in the sense, it will be approximately converted into 0. For example, first 2 layers it will update properly, 3 layers it will update properly, 4th layer what will happen in the sense, due to some computation changes in the propagation, during the back propagation, what will happen in the sense, this particular value, if it's going for 100 time steps in the back end in the sense, it will be getting it as a 0. So once it is getting 0, what will happen? Your entire architecture will be multiplied with the values of 0, and obviously you will be getting vanishing gradients. Your architecture will go to the loss of 0 or less than 0, something else. So somewhere you will be having a loss this one, and when you are sometime you will be having a loss as like some 1.2 something, consider 1.2 to 3. So over the time period of 100, it might be raised to some 3.4 something else. So that means your loss will be growing like anything because your weights of each and every layer will be increased like anything. So obviously your gradients will go very high. Okay, this is how exploding gradient and vanishing gradient problem, how it occurs. Okay, this is the same thing I have. So okay, in order to handle this, we have the concept called LST. Okay, long short term memory. Okay, this is how we brought the concept called LSTM and as well as a GR. So we'll discuss one by one. So vanilla RNN gradient flow. So LSTM before LSTM when it came in the sense it's time of 2013 it came. So before that we have the RNN architecture available. But we have the RNA architecture for some text classifications and everything, and we were using the approach called BPT, so back propagations through time. So we are using the back propagation through time. So you can ask, okay sir, you said like we are using the back propagation through time, but you are getting the exploding and the gradient problems and all, exploding and vanishing gradient problems. How will we handle it? We were not handled by using some some logs, by using some weight changes, by using some module changes. We have managed to do that. But after 2012-2013, they have started to introduce LSTMs and GRUs. So how this makes sense in the sense, maybe first we will discuss about vanilla RNN. So now consider this is your cell. Okay, this is your simple RNN, the one we discussed. You have a previous state information and the current state, we have a respective weight and we are multiplying them and you are getting the next state information. So this is a process. So this is how the equations we have formed previously, and in order to compute this we have a common weight. this is a tanh of one weight. So only one weight we will be using for the previous state and for the current input state. Okay, so this is a vanilla RNN we have approached, but in so this is the same. So this is how the process will happen. The communication will happen. Okay, so now how this LSTM makes sense. So what is the purpose of LSTM? Okay, sir. Now you are talking about LSTMs and all. What is the main purpose of the LSTM? Why we have introduced LSTM cell into the RNN? Reason is, earlier, if you are giving this overall sentence to the RNN architecture, vanilla RNN, we consider all the values and it will take all the values equal importance and it will be doing some classification. You will not do any contextual based understanding. You will just do the tokenizations and it will do the process. But by using vanilla RNN, it is started to give the importance of only the top words of your overall data. So now if you see that in this data set, in this particular data set, what is all the important word? One is amazing, another one is a perfectly balanced breakfast, and will definitely be buying again. So these are all the three factors are very important. So it's in order to understand this overall sentence, I don't need to understand each and every words of this. So in vanilla RNN, what we have done in the sense, we will be considering all the values together and we will process it. Even though we have approached BPDT approach. But in LSTM, we have brought the things, we need to store some information. Anyway, we need to store some information. So while you are storing, focus on only the high weighted information. So out of this one, just do some basic NLP concepts, we do some basic NLP concepts, and based on the word frequencies, we can take those values, and for those values, you can just do the classification. The same approach in advanced way we are using in the LLMs, in the transformers. The same, similar approach, but the approaches are different. Okay. So now, long short-term memory. So what is a long short-term memory? In the sense, this is how your long short-term memory looks like. Maybe the definition wise, LSTMs are explicitly designed to avoid long-term dependencies problem in order to store some information of the previous state to predict the new value for the next state. That is a long short-term dependencies and well suited to classifying, processing and making predictions based on the time series data, since there can be lags of unknown durations between important events in the time series. Yes, of course. When you are working on a time series problem statement, so we may have to consider the previous informations to predict the new version. But sometimes we will be experiencing some lags due to some durations kind of things, because we are not going to consider all the informations to be stored together. Only the LSTMs is capable to store few information, maybe up to 1000 words. We have only the capable to store up to 1000 words. I mean, deal with the 1000 words. So during the dealing with the 1000 words, only few amount of data only we can able to store in the backend. Okay, and that's developed to the exploding and vanishing gradient problems that can be handled during the time of processing. So exclusively we have introduced this LSTM cells. Exclusively these LSTMs is resolved of exploding and exploding gradients and as well as vanishing gradients. How it is in the sense? Cause of these cells. Okay, so this is how your LSTM looks like. In simple way, exclusive pictures I have, I will show you. So this is how your overall LSTM image looks like. Okay, this is how your overall LSTM looks like. And if you see here, this is a vanilla CAD. So sorry, vanilla RNN. Your vanilla RNN will have a common weight which is multiplied with the previous set of information with the current time state. This is in order to predict the next hidden layer information, next hidden layer values. But when you go for LSTM, it will be having a 4 data. It will be having a 4 cells. So one cell is like a input gate, forgot gate, output gate, and next one is a gate. Okay. So what this says in the sense, input gate, you can give the information. It will take all the information, and it will define what are all the data needs to be forgotten. Okay. Let's consider with this picture. You will be giving all the information. Okay. You will be giving all the information, and it will define what are all the inputs to be taken. And the forget gate will define what are all the data needs to be forgotten. Okay, and the next one, output gate. So once it is forgotten, in the sense we have some set of values. What is the output need to be given for the next cell? It will define what are all the output need to be written for the next cell. And the next one is like a gate. How long the data you have to return. Okay, this particular gate will define how much of input you have to return. For example, as I told earlier, RNN is capable to handle up to 1000 words altogether. So when you are given this overall text, you can able to handle maximum from this sentence to this sentence. You cannot able to handle all the data. Okay. In this data, it will be taking into the one cell. Once it is taking into the input cell, we are considering it as an input cell, and we will be defining what are all the data to be remembered and what are all the data needs to be forgotten. Okay, so once this process is done, what is a very important value? Amazing is an important value. So that amazing will be written into the next cell. Okay, so this is how this 4 gate is playing a vital role. Okay, so how these 4 gates are equation wise is nothing but in order to calculate the next cell state information, in order to calculate the next hidden state information. This is an equation. So in order to calculate the cell state information, this is an equation. I'll explain this equation in detail. This 4 gate is clear, right? Input gate, forgot gate, output gate, and gate. Okay, because if you give 10,000 words, your RNN architecture cannot accommodate all the 10,000 words to do the process. If you give the overall sentence, it will take only the few sentences to the gate information, and that will be considered as an input. And in that input, what are all the data to be remembered and what are all the data need to be vanished off. Okay, so based on that, the remembered information will be given to the next cell. For the remembered information, you will calculate some hidden values. Okay, that information will be given to the next hidden values to the other layer. This is how this gate process will happen. Okay, so now if you see this LSTM, this is an overall equation represents looks like. So you have LSTM. Okay, so you have LSTM. So now this is a cell information. So in particular LSTM, what data needs to be remembered and what data needs to be transferred to the next cell. That will be handled during this streamline, and the hidden values of this particular cell will be defined by this stream. So previous cell information, so hidden state values, and what is a new hidden value needs to be transferred to the next cell. So likewise. So now if you given, maybe if you consider with this particular line, consider you have given this particular line. So now in this line, it will take amazing, this Sarah is a good kind of things, and it remembered only the amazing. That amazing will be given to the next set. For that amazing, it will calculate some weights. That weights will be given to the next set. Is it understandable? Okay. Okay, this is our overall equation. Equation wise, if you see, like we have a current cell state information. This cell state information, which is equal to how much needs to be forgotten based on the previous cell information plus what is the input with respect to the current cell space. This is called this equation. And the next one is like a hidden values. Okay, based on your output, it will be having the tan H equation. So tan H equations is nothing but how to calculate the negative values, -1 to +1, right? So based on your output, it will be calculating the hidden values. That hidden values will be given to the next cell. Okay, so here max minus C T minus 1, H T minus 1 is the previous cell information, and C T and H T is the next cell information per time step. Okay, so this is a LSTM flow generally will work, and so uninterrupted gradient flows. So doing this process, you can able to reduce a lot of gradient problems. Reason is nothing but earlier in the vanilla RNN we don't have a right approach to process the data to handle the hidden values or something else. But at this place we are having a various cells what needs to be handled with each and every data. So once you give an overall input, how this input needs to be stored and how this input needs to be converted into the hidden values and needs to be found. So we have some common community, common cell to handle this. So that this is a structure which helps you to handle the vanishing and exploding gradient issues. So GRU is a other cell. So how we are working with the LSTMs, right? So likewise, you are having the GRU cells. GRU cells is nothing but gated recurrent unit. It is almost similar to LSTM, almost close similar to LSTM. Earlier, we have a multiple cell state. LSTM is slower. Reason is, if you give one particular sentence, it needs to do the lot of process with respect to cells. That means each and every cells need to do multiple processes. It needs to take what is a cell state. Based on the cell state, it needs to accommodate the words. And once it's accommodated the words, it will be considered as an input value. That input value will be given to forget gate, what are the data to be forgotten. So once it is forgotten, that data need to give it to the output gate. Likewise, multiple processes are there. Within a cell, with a lot of synchronizations will happen. But when you go for the gate recurrent event, they have brought a one concept called why we have to understand what is a cell capacity. Okay, so why we have to understand the input capacity, input data and everything. So input and everything we are manipulating through the architectural starting place. Just to give the data and update what information is required. And another one is reset gate, update gate, reset gate. Reset gate will forget, just to forget the information and have the information, just pass it to the next system. That's it. Okay, you can ask me why they haven't done in the previous LSTM, because LSTM is a first cell which is introduced in an RN architecture to handle it. That's a older model. So there is a furnished model is a GRU. That is the reason. That is not different. So what is after GRU? Now we are talking about attention models. So earlier, because attention model actually created by the Meta. Meta is the one who created attention mechanism, and instead of these cells, they have created their attention mechanism, attention models, and replaced them. And there is a lot of drastic differences made across all the applications. But what Google does, they are very smart. They have taken the attention mechanism concept, they have created one paper called Attention is All You Need, and they have created one LLM architecture, and that means a transformers. The attention is a matters. They have understood attention is a matters. They have created a complex architecture. And parallelly, NVIDIA was started to growing, and as well as AMD also started to grow like anything. So they have created a complex transformer architecture. They have implemented as a paper, research paper as attention is all you need. Now we are talking about a generative AI and tools and everything, right? Everything started by the single paper called Attention is All You Need. It is released at the time of 2017. But 2019, because I started to work on 2021, these LLM models. So 2019 it became so famous with respect to some basic LLM models, because I was worked on very basic BERT models, very basic BOT models. But after that it became so famous. That single paper make the entire revolution changes in the AI field. So that is the reason it's going unstoppable. That one paper makes the AI field is going unstoppable. Okay, so this is almost the same to the LSTM architecture. This is how it looks like. So LSTM, we have 4 different states to handle each and every input, because we have to concentrate on each and every values to be processed. But in GRU, they have made it as a very simple, just a update, just a reset. Reset to be forgotten, update to be sent into the next cell information. That's it. Okay, here also we'll be having the same, like a cell information, hidden information will be there. Okay. And so what are all the applications of RNN? So one of the premium application is about like image captioning. That's all. Whatever the things you worked at 2015, 16 and all, right? Everything is a RNN architecture, image captioning. I mean, what is that? Google, what is that? One application. I forgot the application. Sorry, Google? Google. Not Google Insight. Google Links. Not Google Links, actually something. Okay, I forgot that. Sorry, no? No, not Google. It's an older application actually. Suddenly it's not coming to my mind. Some time ago also I remember. So that's all. Once you give it some image, it will be giving you the captioning. So we have multiple applications. Once you give it some images, it will be giving you the captionings. So this captionings, everything is based on RN architecture. And another one is like time series prediction. And what are the applications? Like some people do ask me, is it possible to use RN architecture for image classification? Yes, it is possible, but it will be taking a lot of efforts. That's what it is, a one way. This is the same approach we have used for image captioning, image classifications and not image classifications, image transitions and everything, right? Everywhere you will be using this combination, RNN for image classification. So what we are doing in the sense, we are using some CNN architecture. So we have a CNN architecture. This CNN architecture, they have used it for extracting the features from the data set. Okay, so some time ago we have done, right? If you are giving the birds data, it will extract the features from the bird data, and that data should be given into the RNN architecture. Your RNN architecture should take that value and should work on the classification. But the big challenge, very big challenge part is, of course, dimensionality reductions, because the CNN architecture will give you the data with respect to 3 dimensionality, but your RNN architecture can accept the data with respect to the flattened data, and also it's expecting in terms of text. and it needs to be tokenized. Likewise, many things are there actually. So in order to handle it, we have to work a lot of dimensionality reduction techniques. So that is a one complex where if you wanted to work with RNN with image classification, some examples I have made it here. For consider this is your image, and from this image you are giving it to the convolution neural network, and finally this will be giving you the flattened results. Okay, that flattened results should be given into your neural network. So just it's not as like this I'm talking like here. It will be taking a lot of dimensionality reduction techniques. So some of the PCA techniques you should use in order to reduce the dimensionalities of those, and also you need to adopt them with respect to the tokenizers. So to make your model to understand, so whether it is a bird is flying, kind of things or not. So rest everything is same. Extracting the features, that features needs to be to some dimensional reductions, that you can give it to the neural network architecture, then it will be doing the process. But one change will be in your equation is like a values, because you will be giving the values, that values will be added. Okay, so this is a traditional equation. On top of when you are using the images, your equation will be mutated in such a way, because since we are working with, though we are doing the dimensional reduction, it is playing with the three-dimensional informations to understand various part of your images. Okay, and so this is a process I have mentioned right here. And image capturing, so these are all the image capturings done by RNN architecture. A cat is sitting on a suitcase on the floor, a cat is sitting on a tree branch, like this, blah 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 blah. Various capturings are there, and some of the failure cases also is there. And in order to handle these failure cases, this is a way where we brought the concept called attention mechanism. Okay, this is a place where they have brought the concept called attention mechanism, Meta brought attention mechanism, right? This is what I'm talking about. Okay, they have brought the attention mechanism on top of the images, but Google's used this same attention mechanism on text classifications, so text generations kind of areas. Okay, so now what is the attention mechanism they have used? In the sense, input image, extracting the feature maps, that should be given to the attention mappings. Okay, attention mechanism. Your attention mechanism will understand all the images, and it will be giving you the attention on only the where high region of interest. It will pick the specific region of interest, and where there is a interesting values, there it will be giving you the attention. So that means when you see the images wise, it will be so simple. So you'll be having images, and you have a bird. So these are all the pixels you'll be having like a 0.1, 0.1, 0.1. But if you go for these pixels, we'll be having high numbers like a 1.23, 2.24 like this. So that is what, based on this value, your attention mechanism will be giving you the attention mechanisms. Okay, and you can see some of the areas are high hard attention, some of the areas are less attention. Reason is these are all the areas we have a more numbers. These are the areas that we have a less numbers. So attention. This is how the attention is helps us. So after attention mechanism, we will be having some values. If you give those values to the LSTM cells, it can able to give you the proper predictions. So this is also sequential prediction. A bird flying over a body of what word by word generations will have. Okay, so that's what, based on the problems they have introduced in it. Okay, RNN architecture, of course you can use it for images also, but you have to do the extractions and feature map extractions you have to do, and then you have to do some dimensional reductions, and you need to give it to the RNN architecture. In RNN architecture, there is some attention mechanism concepts are there. If you introduce that attention mechanism, you can able to highlight, you can able to get the more information about the region of interest, exclusive region of interest of the images, and with that value, you can give it to the LSTMs. I mean the RNN architecture. Now your RNN architecture can able to understand that will be giving you the predictions. Okay, these are all the separate technique. Before giving to RNN, you have to do convolution, you have to do the attention mechanism. That attention mechanism results, you should give it to the RNN. Okay, so this is how actually back. If you're doing some projects in a CNN, or if you're doing some projects using attention mechanism in a CNN, you can able to see these differences. How it is providing you the attentions based on the region of interest we are playing around. Okay, so we are having a soft attention and a hard attention. So soft attention is nothing but in which area you want to. If you are looking for some wide range data in the sense, soft attention is fine. But if you are looking for some precise area information, if you are looking for your region of interest is a very peculiar, for example tumor, so cancer classification kind of things, in the sense your area of interest is a very peculiar, at that moment you should go for hard attention to get the better and accurate results. So these are all the overall results. Like everyone is throwing a frisbee in the park. Our dog is standing on the hardwood floors. This is everything. Okay, this is a missing value prediction. So this is the same thing we'll be doing in a transformers and everything. Okay. So why am I showing this in the sense that actually this part is not required for you people. The reason for showing is nothing but, so if you wanted to do any projects, iron using some image classification, yes, there is a possibilities, and we have a lot of papers in order to do this. There is a multiple applications also is available. I have one source code relevant to this RNN using the image classifications. I can show it with you. Maybe it is in a repository. You can take it up and you can do some projects. That is also will helpful. Okay. So what else about this is that you can go for hands-on of RNN using sentiment analysis. Any doubts after this? So RNN sentiment analysis, this is the repository. Artificial intelligence. Artificial intelligence. RNN sentiment analysis. This is a source code. You have to load. Artificial intelligence sentiment analysis. Here we are going to discuss sentiment analysis RNN. So this is my repository. The source code we are going to discuss is a sentiment analysis RNN, and another one a sarcasm data. So first we can see sentiment analysis RNN. This is source code, maybe it is sentiment analysis R. Sentiment analysis R1.it. The naming is same actually. For the folder name and as well as the file name would be same, so that it confuses. Sentiment analysis RNS.IPOA. Actually, this source code is so simple, but before this, you should know some knowledge about NLP. So in my data set, so in my repository, there are like NLP basics and NLP. Anyway, I can just explain this. You don't have to try this anyway because NLP is other technique to handle your text classification. When you wanted to work with the interval text and everything, there is a NLP. For example, you have images. You cannot able to give the images straightforward to the architecture. Before that, you will be doing some pre-processing. To do that pre-processing, you will be using OpenCV techniques, computer vision. So likewise, we are having for NLP, we have NLP technique to handle your text data. So because we have multiple things are there, like a tokenization, patch sequences, and text sequences, and lematization, stemming, many techniques which is available in NLP. But I'm not taking everything just for just to understand the sentiment analysis of RNN. You should have a base knowledge about the RNN. So NLP, just to tell it faster. I don't want to take much time on this. So now if you see, from TensorFlow pre-processing, I'm using the tokenizer. So what is a tokenizer in the sense? Your architectures, even in your architecture, even in your NLP, so even if you go for transformers or LLMs, everywhere, okay, everywhere you might have seen this particular word, this NLP techniques, because your architectures would not understand your text as a text. Okay, so it needs to be converted into some numbers. If you convert it into some numbers, that numbers should be in some vocabulary. That should be in some standard format which makes your model to understand. Okay, so randomly, okay sir, this is Jai Ganesh, I have a name. I'm changing, this is a 1, this is a 2, token is a Jai is a 3, Ganesh is a 4. Likewise, you should not mention in such a way it's a randomized number. Because each and every number should have some meaning to represent that particular name or the text. So similar way, in order to do the same process, we have a package called Gensim, and we have some of multiple NLP methods are there. So here I'm just going with the TensorFlow tokenizer method. So now you see, this is your data set. Consider, this is your sentiment analysis, this is your data set. I love my dad, I love my dog, I love my cat, you love my dog, and do you think my dog is amazing? Likewise, you have 4 different sentences, and I wanted to tokenize them. And if you see this picture, like a tokenizer, I'm creating the object. Now I'm transforming fit on text. Okay, I wanted to apply the tokens on the text you are seeing right here to the sentences. And now by using the token, I'm seeing the indexes. What is the word indexes? Now if you see, you can able to see my is a 1, love is a 2, dog is a 3. Likewise, it will be creating the word index. Now henceforth, if you wanted to understand your RNN architecture or your LLM model about, if you wanted to train your LLM model, or if you want to train your RNN model, if you want to train with the amazing word in the sense, you should take the word from here. So 10 in the sense, according to your RNN, it is amazing. According to your RNN and LLM, the word number 6 in the sense, this is a cat. This is a called vocabulary. Okay, because now this is my overall data set. Okay, from this overall data set, what I'm doing in the sense, I'm making one vocabulary. So overall my vocabulary length is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So overall 10. My vocabulary size is of this one is 10. Okay, my vocabulary size is 10. Okay, and also even we have other thing is like a frequency, word frequency technique is there. So what is a word frequency in the sense? Word and a frequency. Now if you see love, 1, 2, 3, 3 words. Okay, and now mind, 1, 2, 3, 4, occurrences 4, and I, 1, 2. And if you say you, 1, 2. Okay, so now if you see dog, 1, 2, 3. So this is how your NLP techniques will understand the data. Okay, so now this is a word index. Word index is nothing but it is you have given the data set. From this data set, overall vocabulary size is 10. How this 10 represents? Because you have only 10 unique values from this data set. Get it? Okay, this is one of NLP. And also, we have other technique called word frequencies. So what is the purpose of word frequency in the sense? For example, now we're going to work with the IMDb data set. In IMDb, it will be like a lakhs of data will be there, lakhs of words will be there. I cannot take all the lakhs of data to train my model for sentiment analysis. So for that, what I'm going to do in the sense, I'm going to take only maximum 30,000 frequent words. Top words is a maximum 30,000 frequent words I'm going to take in order to make my model to understand for predicting sentiment analysis. So what is the top words that you are meaning? That means consider this in this data set, this is IMDb data set. I don't want to train my data set, my RNN architecture with all the data. Instead, I'm taking top 3 words. Top 3 words in the sense 1, 2, 3. My love dog. These are the 3 frequent words and these are the 3 top words. So I'll train my architecture with RNN architecture only with 3 words. This is enough because mostly these are the values are repeating in your data set in the sense that is a word which communicates some emotion about your data set. So amazing is coming everywhere in the sense in your movie analysis. Okay, amazing in the sense okay, the movie is amazing. The bad, ugly in the sense it will be there. Ugly many times in the sense that is the maximum. So that means these are all the words which plays a dominant role on top of your data set to share some emotions about the data sets. Some emotion about the movie analysis. Am I clear? Am I clear or am I confusing? Okay, so this is a one way of NLP techniques, and the next one is a padding. So tokenizer is done. So what is a padding in the sense? Now this is your data set. Consider this is your vocabulary. So if you proportionate of the vocabulary is of course 10, and now you are doing the tokenizer out of vocabulary. I have mentioned as a null. Okay. So if there is any word is not present in your vocabulary, we will be tagging them with the 1 or 2 something. 1. Okay. Now tokenizer fit on text and word index. So now I have a word index. This is my word index, and out of vocabulary is 1. For example, the new information is coming. You know, model is completely trained, and you are putting some question. Extra fab. This particular movie was extra fabulous. You are giving, but the extra fabulous is not even trained with your RNN architecture. How it will handle the extra fabulous? At that moment, it will add for the particular word with the value of 1. That means that particular word is not even trained with your data sets. In your data set, the extra fabulous is not present. Out of vocabulary, that particular word. So that is what we will be having a out of token value of vocabulary is a 1. Okay, and the sequences. Each and every sentences. Now you see. Now you have like a I love my dog, I love my cat, you love my dog, and do you think my dog is amazing? So now 4 sentences are there, and we have a 4 different sequences. 4 different sequences. That means I love my dog. 5, 3, 2, 4. Where it is I? 5. 5, 3, 2, 4. I love my dog. Okay, likewise, another sequence. This sequence is converted. And the third sequence you can see, it is a common word. Why it is a common word? There is a comma. Okay, so I think it is not ran with this, and it ran with this, I guess. Because there is no comma. Okay, there is no comma. That's what it was taken entire word as a sentence. I think so. So entire word as a sentences. So this is how the sequence has been created. Now the next one is like a padding the sequences. What is a padding in the sense? Nothing but, for example, if you see one particular word, if you see a maximum the data in the sense, I am doing the padding, I am mentioning it as a padding equal to padding sequences, maximum length up to 5. So whatever sentence it would be, I wanted to take the maximum sentence to be formed as a 5. 5 is a maximum sentence length. Here you can see I love my dog, maximum 4 is there. So in order to match the padding, I wanted to have a one padding value is a 0. So that is what I am making it as a padding as a 0 right at this place. Okay, for the second sentence the same. For the second sentence maximum 4 word, the padding I am just doing it a pre-padding. This is called pre-padding. Okay, this 931 is nothing but because all values are considered as a 1 sentences. But since I mentioned as a maximum padding length is a 5, it is taking a last 5. Okay, this is a padding. So this is all simple NLP techniques which you need to aware of. And what else? This is also same. I have a data set. I really love my dog. My dog loves my house much, and I'm creating the test sequences. The sequences are nothing but these 2 sentences, make it as a sequences based on a word indexes. And the next one is a padding sequences. But here you see maximum length of the padding is 10. I mentioned. That means the length should given to the RNN architecture maximum 10. So 10 padding pre. Pre in the sense I wanted to do the padding before the values, before the actual values. So 5 values are 5 characters are there, and I wanted to make the padding as a 10. So I'm given as a pre, so that 5 zeros before, after 5. And here 6 characters are there. 6 characters in order to make a padding length as a 10 pre padding. Okay, so this is a simple thing in order to understand the. Just give me 1 second. Okay guys, shall we play a small game? Just for 10 minutes. At least that game which helps you to understand something. Because obviously, I'm not sure how far this RN architecture is going to help you. At least that game will. At least you do remember the person is came and he played this and you go. Okay. I need 3 volunteers. Don't think like I'm not asking about any session related questions or something. It's very common. I need 3 volunteers. Any 3 volunteers. Just 10 minutes. Sorry. Any 3 volunteers. Don't worry. I'm not asking anything and I'm not making you laugh by others or something else. Just like I need your opinion. Any 3 volunteers. Volunteers. Come. Come. Oh, the event got understood. Okay, no. I'm asking for volunteers to play some game. Yes. I need 3 volunteers at least. Any 3 guys? Come on. Guys, come on. Come, bro. Come. Don't decide, guys. I'm not going to do anything. I told you, right? I never hurt anyone. Okay? Any 3 volunteers, seriously, this game will make something to make you understand. Any 3 volunteers. Boys. Any 2 guys? You want to without no? Yeah, not a big deal. No. Yes. Any one thing. Okay. It's a small game, man. Small game. It is about like I'm going to offer you 3 boxes A, B, C. You have a dream house. Okay, your dream house or dream car, whatever it is. For your dream house, for your dream car, I'm keeping the key. I'm keeping the key anywhere in the boxes. Anywhere in the boxes. Which box you wanted to choose? One by one. Your name, ma'am? You, ma'am? So you can also choose the same boxes. Not a big deal. Your name, ma'am?
Jane.
Yourself, bro?
I choose it C.
C. I choose B. C. Raghav B. Okay. For 2 minutes, if you can stand beside the place, ma'am, I'll call you one by one. Okay, you also. Outside. This is the 2 minutes. So, now you see, this is a game I offered them a 3 box, and each of them have chosen a different boxes. Okay. Now I'll call them back, and I'll give them other option. So what I'm going to do, in the sense I'm going to offer another box called X. In that box, I'm going to keep a key. I'm going to ask them, do you want to change your opinion, or do you want to change your option or something else? Most of them, maybe out of three of them would stick with the same points. Out of three, maybe only one may change. May they have chosen for the Xbox. But mostly everyone will be fixing with the same boxes. Just consider, now you are all God. Now you are the future knowers. Now you know what is their future is about. But what we will do, you all will scream. You all will scream to your friend, choose A, choose A, choose A. But you will not able to listen. And some people will be telling to the rest, like, this is your future, this is your future, you people will be saying anything. But they can't able to listen. Okay? But let's see what they are picking up. Mostly, as I told earlier, right, they will be sticking with the same points. They never choose new boxes. Same box. Let's see. They will change. If it is perfect. Okay, let's see. Now, Vidhu, ma'am. Vidhu. One by one. Ma'am, I'm going to offer you a new box now. There is a box called X. There may be a chances of keeping the key in the X box also. You wanted to stick with the same, or else you wanted to change the different box. You want to stick with the same, the box C. Okay. Take your place, ma'am. Thank you. Jai Shri. Jai Shri. Sorry, ma'am. Jai Shri, ma'am. So I have other box from here. So there may be a chances of your key will be there in a box of X instead of B or A or C, something else. You wanted to choose a different box, or you wanted to stick with the same, ma'am? You want to stick with the same? Sure, ma'am? Okay, thank you. We can take it. Thank you. Raghav. Okay, hi, Raghav. I'm offering you the new box here. The name called X. Your key may be the chances of keeping in a different place in the X box instead of A, B, C. Okay, you wanted to stick with the same point, or else you want to change the box. What do you like to choose?
Previously, my key was there in any of these.
No. It might be, there may be a chances of available key in Xboxes also. I'm offering the new box. You want to stick with the same, or you wanted to switch? What do you want to do? You will change to X. Sure.
Since you said there is a possibility of changing
Okay, thank you. Sure. Thank you. Take your seat. Thank you. So that is what. So what is the game in the sense? As I told, two of them, ma'ams are picking the same boxes, and he picked the new box. So what is the concept in the sense? Nothing but one. So generally we all, apart from you people, everybody knows, I have changed the key in the boxes of X. But most of us, we will not be changing our opinions, we will not changing our mindset, because once we stick it, this is what the world taught us. Even I myself also, when I played the game, I was sticking with the same box what I choose. Because the entire nation, entire country has sticked with, once you've taken something else, you need to stubborn with it. It's not required, we need to stubborn with all the stuffs. We have to loosen up. We have our various options. We have to go for the various options, nothing to lose. What we will lose? Some money we will lose, some respect we will lose, some dignity we will lose, something else will happen. But at last we'll have some experience, we have some new futures. So that's what I try to say. Whenever you are getting a new opportunity, always be open. Something is coming into you. It may come to you to teach something. It may come to you to change your entire future itself. Always be open and try to adopt with the new changes, because the new changes obviously will make our life changes to different. So that is what. So that's what I said. Most of the people will stick the same points, and some of them may change. I am also including the same case anyway. So because this is what we have been trained on. Okay. So always, whenever you are getting an opportunity, go with them, because most of the people are sitting right. How many of you would pick the same box? Guys, how many of you would fix the same box? Honestly, most of you I know. Okay, because this is what even I also the same. Okay, you will change if it is perfect. That's what opportunities comes from anywhere. Okay, so that's what I wanted to communicate this one. Is it clear? This point is clear. Can I go to the next one? Thank you, ma'am. Thank you for the participation. Thank you both. So now let me take it to hands-on part. So this RNN part, we have a cloning the repository. I'll go a little faster. We are close to the time of time. Just bear with me 10 minutes, guys. Sorry for it taking your time. At what time your college is? 2:45 or 3 o'clock? 2:45 hour. I'll take maximum another 5 minutes. 45 to 50 maximum. Okay. Bear with me. Okay, I'm sorry for it. So I'm having a cloning the repository. Next, as usual, I have a NumPy dataset. I'm going to use a IMDb dataset because my problem statement is about sentiment classification. Whether a movie sentence, before you are giving some feedbacks or you are giving some words about the movie, whether it is a positive or negative. This is a classification we're going to do. So in order to do this, you are using an RNN architecture, and this RNN architecture will understand your text based on some NLP concepts, and it will be giving you the predictions. That predictions is all about whether it is a movie is a good or a bad. This is our problem statement. Okay. So IMDb sequential, where we're going to construct our architecture, dense LSTM, and embedding dropout sequence. This is all I'll tell you later. So next one is like a random seed. If you see this line, numpy.random.seed. Okay, so that means 7. Nothing but it is like a randomness. Creating the data set, you have a 100 data set. I'm creating the randomness between a 7 data, somewhere data from some 7, somewhere 7. Likewise, I'm picking the data. It's like a shuffle. Okay, more or less it's like a shuffle. And the next one is a top 5,000 words. So now, as I told earlier, right? If you take a data set, totally we will be having almost ample number of data, ample number of words will be there. Sentiment analysis like multiple words will be there. But I'm not taking the entire vocabulary. Actually, the vocabulary size of your IMDb is, it comes like a 2 lakh of data, I think. So I'm not sure whether it is changed or something else now. But it comes like a 2 lakh of data. Okay. But now I'm going to choose only the vocabulary size as 5,000 because I'm not going to train much, because I'm not going to create any real-time model. That's what I'm taking the top 5 words as a 5,000 words. So now by using that 5,000 words, I'm loading the data set, creating the training data, testing data. That is done. Next one, maximum review length. Okay, the maximum review length, I'm setting it as a condition as a 500. Okay, the maximum review length supposed to be 500. If you are talking about some movie, maybe you shorten some of the word length, maximum 100, some of the word length maybe 200 or something else. But in this place, I'm keeping it as a 500. If some of the sentence is not a 500, what it will do? Adding the padding. It will do the padding. Okay, so that is what maximum review length. I am taking a 500. Now, next one, sequence from the function called the sequence. I'm doing the pad sequences. I'm taking the training data and the maximum review length. I'm just doing the 500. As I told earlier, if your movie review is not a greater than 500 in the sense, it will be keeping the padding as a 0. So that is the 2 lines we are doing, extrain and the extest. The reason is this extrain and the extest is the data, and the white train and the white test is the labels. Okay, that is what I'm doing the padding right here. And next one is like a dimensionality. So now if you see here, embedding vector length is nothing but 32. So what this 32 says in the sense, for example, the movie is good. This is how the text. Okay. Now we will be tokenizing this word to 1, 4, 3, 2. Okay. In order to represent this one word, you will be having the vector length of 32. You have a vector length of 32. In order to represent one word, it will be having the vector length of 32. That is the embedding values of the particular word. Okay. That is what we are mentioning as a vector length. How many vectors you wanted to consider for one word? Okay, so 32, and creating the sequential architecture, sequential API. I'm creating the sequential API. In that API, I'm creating the embedding layer with the 5,000 words, right? So 5,000 neurons, and each word with the 32 vector. So each neuron with the 32 vector. So 32 vector size. And the next one is the input length. It's like a maximum review length. Input length is a maximum review. That means 500. Okay, so now I'm creating the embedding layer in such a way. I'm creating the embedding word, top maximum 5,000 words. Each word is a 32 vector, and the input length is like a 500. Maximum input length is a 500. Likewise, I'm creating it. And next one is a dropout. So what is a dropout in the sense? As I told earlier, I'm dropping out 20% of the neurons when you are processing in order to avoid the overfitting issues. Next, I'm adding the LSTM. LSTM is 100 cells. Think about it. 100 cells I'm adding. So 100 cells like a 1 LSTM, 2 LSTM, 3 LSTM, like this. I will be having a 100 LSTMs. And the next one is a dropout. Each and every LSTM processed, I am dropping the 20% of the neurons to avoid the overfitting issues. And recurrent dropout in the sense, for each and every LSTM, after each and every LSTM, I am dropping 20%. That's what I'm defaultly given as a recurrent LSTMs. Okay, and now you can see model.den add dense as a 1. So that means only one output, whether it is a movie is a good or bad. Okay, and we are using the activation function called sigmoid. Sigmoid is a binary classification, 0 or 1. So that is the scenario. And as usual, model construction is done compiling with the loss function as a binary cross entropy since it is a binary classification, and Adam optimizer since it is relevant to, because I'm not specifically what learning rate to be given, I'm using the Adam matrices. I wanted to classify only the accuracy at this place. After that, I'm just doing the model. Somebody skip this part. I'm training my model.fit, training my model, and I'm evaluating my model. I'm showing the results. That's it. Okay. Now you can ask me, okay, sir. Now you are showing the accuracy. You are telling the model accuracy is around 75%. How we can able to test it, sir? I wanted to test my data. How I can able to test it? So that is what I'm having the manual data implementations here. So in the below of the code, you can able to see there is a manual value data implementations. Here, similar imports. I'm just loading the IMDb data. Get word index from the IMDb data randomly, not randomly, taking all the word indexes, and from the word index, I'm reversing the mapping of the words. Reversing the word index. I'm taking some particular words with the reversed format, and after that, this is my sample question. So now RN, it's not much complicated, nothing, but I have considered the RN architecture is done. Okay, now I need to put a question. For that questions, I need to do some NLP things, and we are padding sequences and everything I have to do, and then only I can able to give it to my architecture. For that case only I'm doing it. So this is my sample review. The movie was fantastic. I really enjoyed it. The acting was great. This is the important input. For this input, I need to do some of the pre-processing stuff, tokenizing the words, converting the word indexes, and padding to the maximum length. 500 sentence, because this is just 10 words are there. So 500 length you have to pad. So once you have done, you will be having the padded input. That padded input you will give to the model. Your model is providing the predictions. That prediction greater than 0.5, we are saying it as a movie is a good. Less than 0.5, this is movie is a bad. So likewise, I'm setting the condition. So now you see your output is like this is a padding output, nothing but. This is your movie is fantastic. That is a 1. So we are doing the pre-padding to handle the 500 length. That's what I was adding a 0 right here. And this is your review, and the predicted is a negative. Your model is not well predicted here. Reason is because I ran the model for only 1 epoch. If you run it for 50 epochs, or if you run it for like 60 epochs, you may get a good result. And the confidence score is a 16%. Okay. So this is, you can able to use it for any kind of recommendation system. The same problem statements I'm using it for GRU also. In RNN, instead of using LSTM, I have used a GRU. This also you can try. If you wanted to try with a GRU, maybe the GRU makes time faster when compared to this. It will make the time faster. So you can able to use a GRU at this place. And this is the same. This is, and this one is most of same. It's a sarcasm data set. Whether the word is a sarcasm or not a sarcasm. So in YouTube and in the interviews and all, we'll be having it with that data set. So you can try with the other kind of source codes. Okay. So anyway, we will use these source codes for sentiment analysis. Actually, RNN for image classification, I don't have a data set code here. Tonight I will put it. Yeah, I have another repository. I forgot the password now. I'm sorry, I'm not able to show it. I tried multiple times. I forgot the password. Maybe today I will post it. Okay, that's also tried with the C14 data set. Okay, any doubts, guys? Any doubts or any queries? Okay. Any doubts now? So okay guys, if no doubts, we can wind up for the day. Thank you so much. Thank you so much for your excellent time and excellent patience. And thank you so much. Have a great day. Have a great rest of the day. And happy learning always. Bye. Good day. Thank you.